Hi, we're going to generate inclusive integer ranges, which might be ascending or descending. There are many different ways to attack this, and I'm not going to go through all of them. In the chat event, we did have a lot of different approaches taken up, and I encourage you to follow the link in the video description to go to the chat log and see what they all were. For now, I'm just going to go through the shortest solution we came up with and the fastest solution we came up with. So, the problem specification is such that we have both the beginning number and the end number in the right argument. The normal thing for an APL function would probably be to take one on each side of a function, probably the beginning on the left and the end on the right. But because of another follow-up problem that was in the same competition that this problem comes from, they elected to have both ends on the same argument. So given as a two-element vector. And that influences a bit how we're going to form our function. Let's say we want to go from 3 to 10. So the method we're now going to use is that we're going to use the 3, and then we're going to have a bunch of 1s, and then we're going to have those 1s added sequentially to the 3 until we reach 10. So this would need 7 1s. Doing a cumulative sum over those 1s, starting with the 3, gives us the sequence from 3 to 10. If we wanted to go from, say, 10 to 3 instead, then we would do the cumulative sum beginning with the 10, and then we would have negative 1 7 times, and that would give us a sequence from 10 down to 3. So then we're now going to figure out how to generate these ones and append them to the beginning value so that we get the sequence that we want. First, let's find out what the difference is between those two values that we are working with. So let's say we have 3 and 10. We write this initially as a tested function. So here is a minus reduction. That is, we're reducing over this vector of length 2 to get a single number. That just is the same as inserting the minus between the two elements. So this is 3 minus 10. There's a problem here with the sign. If you're going from 3 to 10, we want something positive. So really we want to subtract in the opposite order. We want to subtract the left element from the right element. We can have a modified version of minus, which is the commuted minus, and we reduce using that and then we get a positive 7. Next up is to reshape a 1. We could do this by, again, commuting the arguments of the reshape function and use a 1. However, in the case where we want to get negative ones, this is not going to work, and we can't use a negative number to do a reshape either. Instead, we'll apply another function. The number of elements that we want is the absolute value of this, and the numbers that we want in our sequence is the sign of the difference. If we were to have 10, 3, then the sign would be negative 1. Now we can take the absolute value and use it to reshape the sign. Finally, we want to prepend the first element, 10 in this case. We cannot just say the first function with concatenation, because we're getting out of sync with how our fork works. For this to work, we want to apply this function to the entire argument, and this function to the entire argument. And then we want all of this as a sort of secondary step. The base function here is concatenation. Before we apply the concatenation, we want to pre-process the right argument to the concatenation, which is going to be something based on this subtraction. And we can do that with the beside operator, the jot. This is pre-processing the right argument to the function on the left with the function on the right. Here we have a descending sequence from 10 down to 3, and here we have an ascending sequence from 3 to 10. The only thing that's missing is the cumulative reduction, and this solves the problem. In the 0 case, that is, when the beginning and ending points are the same, this subtraction gives 0, the absolute value is 0, the sign is also 0. That doesn't actually matter because we're reshaping to length 0, that's an empty vector, concatenating the first element, that would in this case be just 10 as a vector, and then we're doing a cumulative sum of that, which just remains with 10, and that's the result that we want when the beginning and ending points are the same. So this solves the problem very neatly, but maybe not the most efficient manner. And the reason for that is that we are generating a sequence here that is not the full length that we want. So we are prepending another element. That means that in memory we have to rewrite all of this data just pushed one step to the right. Furthermore, if we are generating a sequence of all ones, then it would probably be represented internally as a bit vector, that is packed bit booleans, and then when we are prepending an integer value, we would have to convert all these bits to integers again. And then of course we're doing the summation, but we can probably not really get around doing one addition for every element. Let's look at a more efficient way of doing this. When dealing with offsets like this, it's a really good idea to use zero-based indexing. APL uses one-based indexing by default. So let's create a little lambda, a function, where we assign to the special syntax a system variable which determines what all ranges are indexed from, 1 or 0. So if we assign a 0 to that, then it's going to be indexing from 0. Here's the index generator. Let's do the indices for an array of length of the argument. Here you can see it begins with 0. If I switch this to a 1, it begins with a 1. So let's switch that back again. Right. What kind of sequence is it we're looking for? We actually have a beginning point and an end point. If we do this subtraction, then we get a range. Of course, it could be negative, so let's throw in the absolute value. Oops, we're missing the right argument here. We are short by 1. It's the fence post problem. We have an inclusive range in both ends, and so the actual range is 1 larger than this. Let's add 1. Now the only thing that's missing is we need to adjust. We again want to start with the first value, and then we want to add these offsets, but in the case of descending, we want the offsets to be negative. So how can we selectively change this to negative numbers? We could, of course, use a conditional, but really want to avoid branches and all the problems that come with branch prediction. Instead, let's take a mathematical approach. That's the traditional way to do it in APL. Okay, let's look at these numbers again. We can see whether or not one is greater than the other by inserting a greater than function between them. So this is a greater than reduction. If they're the same, we get a 0, and so too if the first one is actually less than the second one. So we now have these two numbers, 1 and 0. 1 for when we need to reverse the sign. How can we map a 1 and a 0 to a negative value, negative 1, and a positive value, 1? A trick that I think a lot of people miss is that you can use power or exponentiation. If you use -1 at the base and raise it to the power of 1, well, any number raised to the power of 1 is itself, so that gives us -1. Raising it to a power of 0 for any number gives us a 1. So now we can use this in our function. If we use -1 to the power of the greater than reduction of the argument multiplied by the sequence we had before, then we get negative offsets when the sequence is supposed to be descending, and positive offsets when the sequence is to be ascending. And if they're the same, then we get a single 0, no offset from the starting point. All that remains is to add the first value to the sequence. And so this is our very efficient solution. Thank you for watching.